like remind her.
All right, we're gonna go over to this slide here. Hey guys, check this out. This is gonna be life-changing, okay? I'd like to show you, let's start with a cardioid, or, well, I don't know, let's start with a couple different limaçons here. How about 3 plus 2 cosine x here, okay? And I wanted to show you something, a point I would have liked to have made yesterday that we didn't quite get to. We started thinking about this a little bit, but like if you just see what I typed in, it's 3 plus 2 cosine x. So what's the minimum and the maximum? Well, this is something we asked yesterday, right? 1 and 5, right? So, and we would ask that question first semester. We asked that yesterday too. We said first semester that would translate to you, if you were to go graph y equals 3 plus 2 cosine x, that would translate to you when you first graph it. You're graphing two horizontal dashed lines that your graph would be contained inside, right? Y equals 1 and y equals 5. In fact, we have the graph of this right here, yes? It stays in between y equals 1 and y equals 5. And yesterday we said that corresponds to the polar graph staying outside of the circle of radius 1 and inside the circle of radius 5, which the graph does. Do you remember this conversation from yesterday? Okay. So I just wanted to show you that that's exactly what's happening here. We can actually kind of see the correspondence between these two graphs from first semester and now in polar coordinates. So where does the big loop happen? Right here, at a maximum. And this part here is where we come as close as possible to the pole. Anytime we're talking about how far are you away from the pole or how close are you to the pole, that's the equivalent of first semester asking how close are you or how far away are you from the x-axis, right? I want you to think about, when you think about the pole, I want you to think about, from first semester, the entire x-axis, okay? So you seeing this happening? It's so fun. Okay. What if we did instead 2 plus 2 cosine x? Well, then now it's going to sit right on the x-axis, right? Its range is going to be 0 to 4. And this is when we get that special case of I don't know why we have a special name for it, just because it's cute, I don't know. But a special case of a limaçon where it comes in and touches the pole, but doesn't cross through and create an inner loop, right? And so you see that on the graph happening right there. See it over on the left and on the right? At this region right there, boom. Comes in, touches, but never creates negative values for r. Let's send that into motion. Yeah? Now let's do one with an inner loop. Let's make this, instead, how about 2 plus 3 cosine theta? Why does that create an inner loop? Well, the range is going to be what for this one? Yeah, -1 to +5. So we get this inner loop. Notice when that happens here. We get here this maximum, which is also this maximum over here, right? Corresponds to the big loop out here, right? And then as we come to here, this is us hitting the pole, and then this, oop, that's the inner loop. And now we're back into the outer loop. Are you feeling this, guys? Is this helpful? I just want to make you understand that as much of a mind bender as all of this has been for you over the last day, honestly, it's really just a recapitulation of the stuff you did first semester on the right. Right? It's just a different way of viewing it. I like to think about take the x-axis, the whole x-axis, and just smoosh it into one point, call it the pole, right? And instead of your graph going up and down around the x-axis, it's going up and down around the pole, right? It's like coming in and out instead of around the pole, instead of going up and down out there, you know? Huh? You like it? Brandon, you missed so much, man. It was so fun. Let's also do a rose curve. How about 3 cosine of 2, no, how about 4? That'll be fun. All right, well, I should have had you make a prediction first. Of course, that has 8 petals, right? And now, Now you can see why we get twice as many petals as well. You see it? Where are they? Well, every other petal is a negative petal, right? Is being created all by negative R values. So we can see that on the graph over here. Here's the first petal right here. Second petal. Third petal. Fourth petal. Fifth petal. Sixth petal. Seventh petal. Eighth petal. And then this is the first petal again. Yeah. You want to do this?
Yes.
Something like it. Draw flowers. This is just the beginning.
I can't talk to me. This is serious right now or not? I'm pretty serious.
Wait.
Fun stuff, though, right? Well, we didn't get to say much about spirals yesterday, so let's use this opportunity to say what a spiral might look like. Let's do, I don't know, x over 2 or something. How's that going to look? Well, on the right, it will just be a line going up. And on the left, it will look like, well, what happens as theta increases? What will happen? So will R. So as we go out, as we turn, we also get farther out, right? So R just keeps going, getting bigger and bigger and bigger, right? R equals theta over 2 would be this graph on the left, right?
Wait, why does it sound like the... Oh, wait, never mind.
Well, there you go.
How do I make it come back? I don't know. It'll come back. There we go. Good times. Okay. I don't have much more to say about that. I just thought, I think that covers our Archimedes spiral. That's called a spiral of Archimedes. R equals theta, or really anything R equals something times theta would be some kind of spiral. We don't need to say much about it. We do? Well, we did. So there you go. This is just, what? It's also like hard to graph on that particular grid right there. We could do it, but it'd be weird. Spiral of Archimedes is what that's called. You can graph it on your calculator. You can do it Desmos. All right, so this is more for kind of fun historical reasons than anything. There's not much we can do with this graph, but it's worth mentioning because it's famous. Okay, so the first thing, again, you kind of ignore the leader text on this for a second, and just let's play around with this graph. I've got one prepared for you here. Imagine that this said, instead of, I'm going to cover up the squared with my finger, imagine this just said R equals 16 cosine 2 theta. What would it be? It would be a rose curve with 4 petals, length 16. Yeah, right? In the 0, in the 4 cardinal directions. All right, so this is different, though. It's not that. It's R squared equals this. So you could also write, if you wanted, I think this is traditionally a good way to write it, but I don't know. I don't see why you couldn't write it as R equals plus or minus the square root of 16 cosine 2 theta, though, if you like. If theta is 0, give me some points on this now. Let's see. Like if theta, let's go for some low-hanging fruit. If theta is 0, we get plus or minus 4 actually, but 1, 2, 3, 4. Or and if theta is pi, if theta happens to be pi, same thing, right? We get 2 pi, 0, 2 pi, same. We'll get the same result here. But anyway, we've got this covered. We're definitely there and there for sure. All right, now let's try theta. Yeah, let's let theta be pi over 4. Right? Yeah, 2 times pi over 4 would be pi over 2, and the cosine. So we definitely beat 0. And now, of course, what would you like to try next? That's somewhat troublesome. Pi over 2 is a great thing to try. Let's try it. What's the issue, though?
Oh, no.
Yeah, so in fact, any time, not just for pi over 2, but certainly pi over 2, But anytime this expression comes out to be negative, we have a little bit of an issue, right? We can't. You could talk about either expression here. If this is negative, well, r squared won't ever be something negative, so that's a problem. Or you can think about up here, you can think, well, I can't take the square root of a negative, whatever. The point is, no matter how you slice it, pi over 2 is a little bit of an issue. Or, again, anytime this expression is negative. In fact, this expression is negative exactly at all the times that rose curve would be creating that entire loop, right? So these loops, we didn't try any of these, but I can just tell you that these loops are perfectly happy and exist. But the other two loops, the other two petals of the rose curve, if you want, it's not a rose curve, but the other two petals, if this were a rose curve, for this curve are kind of like imaginary, right? They just don't exist. And if you watch this graph on your calculator, feel free to try it. Type in on R1 the square root of 16 cosine 2 theta. You'll actually watch this happen. You'll actually see it plotting it happily, and then suddenly your calculator will look like it's dead for a second. And then it comes back alive and keeps making the rest of the curve, and then it goes dead. So during those times when it's dead, it's thinking, it's trying to plot, but failing to plot those other two petals that aren't really there. So just a historical note about this as well. This is very reminiscent. I think this is maybe the symbol that we use also for infinity, kind of, with the inspiration for that symbol at least. Good question. There's so many. I don't know. Yeah, that's a good question. What happens if we replace, just do the same problem again, but instead of cosine have a sine here? What would that do? It actually wouldn't be 90 degrees. Yeah, it'd be a 45. I mean, think about what would, again, without the squared here, what would that look like? Think about the warm-up today. We even had a rose curve with 4 petals that were pointed in those 4 directions. It'd be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, except wait, only these two, right? Only the pi over 4. It would look like that instead of this. It would be in these 2 petals. There'd be 2 petals still, but they'd be in the pi over 4 and the 5 pi over 4 direction. Just kind of a historical note. And by the way, this is called a lemniscate or a lemniscate. I don't have a good read on. I think people are. Yeah. Yeah, it makes you a little bit hungry. Okay. Yes. It looks nice in rectangular coordinates actually as well. Anyway, just thought you should know. In bold, there's a sentence that tells you what the geometric definition is. If you wanted to construct one as a geometry student and you knew nothing about analytic geometry, you could actually construct one by just applying this following rule to 2 points, 2 focus, 2 foci. You could actually construct this using, in the same way you did like an ellipse or something, applying this very strange rule. You get this shape. I don't have anything else to say about these. Let's move on. You ready to talk about the very culminating moment of our graphing experience? Lines, yes. It doesn't sound as exciting as you thought, but we do have a few things to say about lines, so you'll allow me to pursue this line of thinking.
Why is that not?
All right, I have a deep question for you. Do you remember, skeptical, do you remember the normal form equation of a line from the end of first semester? Maybe you do though, maybe you do.
Cosine phi, sine phi, that's all.
Yeah, that's helpful. There's a phi, there's a sine and cosine of phi, true story. Yeah. There's a
Oh, I think I know.
There's a p involved, yeah.
I somewhat remember.
Okay, go ahead. I'll be impressed.
Isn't it like the length of the normal line times cosine phi plus?
No, but yeah, the p is the length of the normal though. Yeah, right. Here it is. You ready? You have it?
I thought I tuned.
Does this look at least familiar? Tell me it does. Yeah. X cosine phi plus y sine phi minus p equals 0. Well, we're not done yet. This is normal form. So that's what we're going to start with here. And now we're going to put this into polar form by making some substitutions. X is equal to what again, class? R cosine theta. And y is equal to r sine theta. So we'll make those replacements. It's irresistible, so we'll do it. Don't you want to factor out an r? And over here, don't you want to move that p over?
Wow, and then cosine squared theta plus sine squared theta equals 1.
Well, it's not cosine squared plus sine squared actually, because they're different arguments.
Oh, yeah.
But it is
One
something.
is phi and one
But
is theta.
it is something interesting though.
Yes, it is.
Namely, what? Cosine of A, cosine B plus sine A, sine B.
Yeah.
Yeah, that's the cosine difference formula for that. So we can tidy this up quite a bit in this equation, and now we'll put it in a box. There it is.
Oh.
Whoa.
Well, okay, so sorry. So there it is in a box. R cosine of theta minus phi equals P, where phi and P, we're using those letters for a reason here. They're the same letters that we used at the end of last semester, and they still mean the same thing. They're what Itai said, P is the length of the normal. Phi is the angle that the normal makes with the positive x-axis, right? So, and R and theta are variables, right? You don't plug anything in for those. Those are not constants. R and theta are R and theta. So, very quickly from normal form from last semester, we can get polar form. So a little walk down memory lane here. So, let's try one here. Let's graph one first, just to get our legs under us, see what this would look like. You don't need a polar grid to do this, just on your paper. You can just kind of sketch a rough picture of what you think this would look like. Keep in mind that I've reorganized the equation a little bit, right? Sometimes you see it the way I just said on the previous page, R cosine of theta minus phi, but equals P, or sometimes we could have it solved for R. Both are popular for different reasons. So how do you interpret the 4? That's P, that's the distance that our line is away from the pole or the origin. And 3 pi over 4, how do we interpret that? That's the angle length that the normal makes with the positive x-axis. So everyone sketch a picture as to what you think it looks like, and I will tell you that you did a good job. Yes, good. Excellent work. Yeah. So, like, this is the way you'll have to enter it in your calculator, you know, for example. So some of you are meticulously drawing the tripolar coordinate system. And then actually draw the line.
Oh, hi, Paul.
There he is. Look at showing. Dapper Dave. Welcome, Tom.
Where's that line I got it?
There he is. So, hey, how did your concert go, you guys?
Did you win?
Do you get all ones, Kate?
Tom, did you win?
He ran. So excited he's in math class. All right, so how does this look? Give me instructions. So you go, it's a line, yeah, that's true. So we go to 3 pi over 4 and then march out 4 units. That's the normal that we just described right there, the segment at that angle, that distance out, and then our line goes like, yay. So give yourself a pat on the back if that's what you said. Good job. Let's get Desmos to do that too, that'd be fun. All right, so on this one, let's do some conversion, and then we'll play around with Desmos for a few minutes, because we definitely want to play around. Alright, this, so that would be bad to not do that. So how do we go the other way here? Excuse me, we'll do both things here. How do we get this into polar form? Well, we're going to have to do a little bit of review from first semester again here, right? But we need to get it into normal form first. We need to identify t and phi, right? So we have to go there. So I might try to get it into that normal form. 3x minus y minus 1 equals 0 is pretty close, except the coefficient on x and the coefficient on y need to be the cosine and sine of something. And right now, 3, that is not the cosine of anything, right? 3 is definitely not the cosine of any angle I know. Right? So we need to divide through by something. And the thing that we need to divide through by is, if you'll remember, is this should ring a bell even more now after having thought about, I don't know, things like unit vectors and stuff like that. We need to divide through by something.
Oh, the magnitude.
Yeah, like really the magnitude, right? We need to divide through by the thing that will make the magnitude of this, like, phasor 1, right? This thing, 3 and negative 1. Or said another way, we need it so that if this really is going to be the cosine and sine of something, then this thing squared plus this thing squared better be 1. Right now it's not, right? Don't you agree that the cosine of anything plus the sine of squared plus the sine of anything squared should equal 1, and right now that's not true. But we can make that true by dividing through by what it is right now. And that's 3 squared plus 1 squared. Take the square root. Right? So then once we do that, is this ringing a bell? We did this last semester at the end. Okay. Once we do that, then we promise you that it is in normal form. 3 over root 10 x minus 1 over root 10 y minus 1 over root 10 equals 0. Apparently that's normal form now. I guess we're just going to trust that that's the case. So p is there for the taking. It's 1 over root 10. Phi is the angle that has a cosine of this and a sine of that. Cosine is 3 over root 10 and the sine is negative 1 over root 10. So we need a calculator to help us here, maybe. What are you doing on your calculator? First one, the calculator. Inverse cosine of 3 over root 10, that would be okay. You'll have to adjust it afterward, maybe. Yeah, maybe inverse sine of negative 1 over root 10 would be a little quicker, maybe, but you can do whichever. Let's see what Francis and Savannah get here. Yeah, are we doing this in degrees? What'd you say?
I got 18.4.
18.4.
Okay, you did.
I don't know. It can't be 18.4 degrees though, because it's in phi is a fourth quadrant angle. Is it negative 18 degrees? People with calculators?
Yep, it is.
Negative 18.4 degrees. Okay. So I think we're finally ready to write the normal form here, or at least the approximate normal form. Keep in mind that r and theta are variables. Don't plug anything in for those. Phi and p are constants, so plug those in where they belong. I think I just see people put things in the wrong spot sometimes. Theta minus, or actually I guess you want to say plus 18.4 degrees equals 1 over root 10. So that's approximately what we're looking for. That seems reasonable, by the way, doesn't it? I mean, think about what this line looks like. 3x, slope of 3x going through negative 1 on the y-axis. Okay, does that look like that would be like negative 18 degrees? Here, let's draw this. Does that look like, oh, that's terrible, sorry, it's so small. But can you imagine that the normal to that is about negative 18.4 degrees down? And the distance there is small. 1 over root 10 is a small thing. Okay. So it kind of makes sense that we're getting this equation and it matches our original picture maybe, even without Desmos. Right, now how can we go backwards? Oh wait, we have a question. Say it again. What about, okay, wait, so what's the problem? You only... Yeah. Sure. Yeah. Yeah. Yeah, you could either adjust this angle or you could adjust the slope here to be -3 or something. Then we could make it. Yeah, I guess it's just a coincidence. The first two examples I've had have been, oh, and this one too. Oh man, we should just change it for you. This one I think also increases. No, they can be any which way. I'll show you in a minute here. We'll wait.
Yeah,
All right, well, on this one, maybe you don't need to know anything about normal form or anything like that. You could certainly do that kind of analysis on this, but you can also keep in mind that this is a problem I would have given you 2 days ago, when before you ever knew it was a line. This is, in fact, I think a problem almost identical to this appears as one of my bonus problems on that inverse the equations assignment from 2 days ago, right? And what'd you do? Well, you just use the cosine addition formula, right? Right, just work this out. Our cosine theta?
minus.
Just testing you. That is actually what I wrote. I think you just having trouble seeing from the back. Okay. Our cosine theta, also known as our cosine theta, x. And cosine pi over 6 is √3/2. Let's see if we still have these things in our heads. Our sine theta, also known as y, and sine pi over 6, 1/2. So in some ways we're done. We could clean it up a little bit though, maybe multiply it. Let's see, so we got √3 times x minus y equals 10. We could even solve this for y. We get √3 x minus 10, I guess. And again, does that seem reasonable for this line? That we'd get like a y-intercept of -10 and a slope of √3 or something? Yeah, I mean, there's the normal right there to the line. Right, and this is our line. I think it seems reasonable. Here you go, phone. That's those up. All right. Yeah, you got to get up. Sorry. There's my grade book. Okay. All right, we're in Desmos. Here we go. We're going to type in, how about, we can do this one. R equals 5 over cosine of theta minus plus, I guess, whatever, pi over 6. All right, what do you think? What do you think? Do you want to change that to something else? Yes, you do. Add a slider for 5? Yes, please.
Please pardon this interruption for some tryout information. Boys' tennis tryouts are canceled for today. Tryouts will start tomorrow. Girls trying out for softball will meet in the main gym at 3 p.m. Boys trying out for baseball will meet on the baseball field at 3. Boys trying out for boys volleyball will meet in the gym lobby at 3. Boys and girls trying out for co-ed volleyball will meet in the small gym at 3. Boys and girls trying out for track will meet on the track at 3. Boys trying out for boys lacrosse will meet in the stadium at 3:45. Girls trying out for girls lacrosse will meet in room 35 at 3:45.
How do you like that?
Girls trying out for softball will meet in the main gym at 3. Thank you.
All right, so the homework, just to remind you, on the sheet is says a couple problems from the book, just a couple, like 3, and then the rest of the homework is this worksheet, and we will not check that until Tuesday, probably, right? Tomorrow we're gonna do career day. Monday we're gonna go over. We're gonna do some stuff with your graph, your IA graphics. See you tomorrow for career day. Huh? Yeah, so the way you catch it is you put your hand up like this, put your hand up, and then I snap it into it like that. You see? You catch it as it, yeah, throw it at 1.5 turn. Not enough. More, give me, so like this. Right? It's gonna snap right up into your hands. Perfect, right? Now your turn. Ready? catch it up here. Yeah, up high, like this.
Wait, did you know evening?
So you can catch it vertically like this, you know. Bye guys, have a great day. Do your homework tomorrow. Oh, you never came back. Right. Yeah.
They were talking about I was going to take
Okay, so over there in the back. Actually, I'll take it back. I haven't put them in there yet.
Well, do you like it on your face when you're all wet and cold?
These two are the ones. One more you didn't get. But we're doing something. You have questions? Yeah. All right. How does he pull out some stuff that will answer your questions? These people are just still here hanging out. This thing's going around and around. That's nice. Looks good. We're still recording.